Day to you. This is Anagalactic bringing you another science presentation. Our broad base is astronomy, but currently we're in another kind of cosmic space. We're attempting to study the inner surface of the universe. We've gotten into the atom and into quantum mechanics, and now we need to study the electron and the proton, because the proton controls space and the electron controls time. Why do we need those? Because light comes from the electron and gravity comes from the proton. And gravity and light are our only two tools. We're going to be doing some things here with this program called Geogebra, which you are free to download. It's open source. And an incredible program, really. I've used it for several things in the past. But I'd like to show you from scratch how to get to this sphere. And just to give you a little idea, this can be rotated. Very nice. That even reduces to a circle, which we're going to want to be using. But Macintosh and Windows, this is available. You just type in Geo, just as in geography, but it's Geogebra. So it's Geo and algebra, Geogebra. And what I'm going to do now is go to the File menu and press New. I don't wish to save this, so I'm going to press Don't Save. And this is a blank screen. Down at the bottom is a keyboard, and I'll show you. This is what you would actually see. This here is default. It's just a grid, and you can turn that on and off, including the plane, the gray plane. We won't be showing general examples of how to manipulate these settings. What I'd like to show you is this screen. You see it's a split screen, and it defaults to more over here. So I am going to type in here, you see where it says input in the upper left hand corner. Now I have something prepared to type in. So I'm just going to show you. This is a surface function that I just typed in. And I haven't pressed return yet, but you see it's already produced a sphere. This is a function that's built into GeoGebra that enables you to type in commands. And now you see I've pressed return and it reduced it. That is, it reduced what I typed in, A, right here, and that's what I typed in, and it put the equal sign in and gave a default name A. I can turn it off or turn it on. So that's rather nice, I would have to say, and I'd like to show you how I did that. What I did simply was to type in, that is, I pasted in that entire sequence. That looks a little daunting. Those of you who've studied spherical trigonometry will recognize what's below it, which cannot be highlighted. It's the 3D parameterization of a sphere. Now, in order to do this, so that you would be able to do it, you have to type a capital S. This is case sensitive, but it's surface. And as you see, as soon as I got to R, it's trying to fill it in for me. As soon as I get to F, it gives 3 versions of the surface command. This is capable of producing several surfaces. The sphere is one of them. There is also a manual of use for this, and quite a few excellent examples online and videos. I learned how to do this from watching a very good video. Brief and to the point, unlike mine. Now, if I highlight this and select it, it fills in for me what I'll want to type in. You have to know what these expressions mean. One would have to look it up, but you can see from up here what this is going to be. Inside the parentheses, the first sequence here, 3 cosine, that is an x value, and there's a comma, then the y value, a sine sign expression. The 3 is just the radius. All of this can be streamlined for you programmers, and I am a programmer. You can do just about anything with this, but this is a simple way to get a sphere. We're going to need this in order to discuss spherical perpendicularity. This part here is the z coordinate. You'll see that on the bottom line in the transliteration. Now the 6 values that follow are for the range, and I have 2 Greek values in here. It puts in the symbol pi. If you type in pi, it'll replace it with that symbol, which is also kind of nice. But for t, which is basically theta in polar coordinates, the lower bound is 0 and the upper bound is 2 pi, and that is tau, and that will draw the entire circumferential range. But then v is also called psi. That's the 2-angle version of. We're using a combination of 2 different formalisms and 2 different representations for getting the sphere. It's built in, so this is a good way to really get a very good grip on trigonometry if you're interested in doing so. But here we have t, 0 to pi, and then for what would be called the latitude, it's v 0 pi. Radius equals, say, 1. And you see it produced a slider. If you don't want to see the slider, you can click on Settings, and there where it says Slider up here in the menu bar, Show Slider in Algebra View, no, and there goes the slider. So that keeps us from having to type in 3 or 1 for the radius 4 times. Good day to you. This is Anagalactic bringing you another presentation in geometry. We're studying the geometry of the universe. That is a bit far-fetched. However, we've made an incredible amount of progress in astronomy in the past 100 years. Speaking now of astrophysics, going to cosmology, attempting to get some kind of understanding of the entire universe at once, which is really asking a lot, I think. But if it can be done, as we here believe it can be, it will be with geometry. It will not be with numbers. And so the efforts of modern cosmologists in getting at the Big Bang are completely misguided. Not completely. It's always dangerous to say completely at this level, because some progress has been made, and in fact, we have very good reason to believe that we can understand the universe at maximum macroscale. That is, the entire universe geometrically. Currently, a false cosmology has emerged. It's not necessary to get upset. Nobody's causing anyone any harm by this. Nobody even knew there was a universe until a century ago. And so the efforts of deep space astrophysicists and advanced mathematicians to solve the equation of the universe are perfectly reasonable, but alas, quite incorrect for reasons which I've described. First of all, we only have one measurement that yields the Big Bang. Everything else is just hot air. There's only one measurement that suggests there might be such a thing as a spatial origin at a point. That's what the Big Bang suggests. But that's based on a mistake. It's an easy mistake to make, and you might think, well, astrophysicists are not known for making simple mistakes. It's not that kind of a simple mistake. It's a simple misreading of a value, which is the redshift, discovered by Edwin Powell Hubble, as you most likely know. The redshift is a linear relationship between cosmic distance and the redshift of the light from that distant object. It's quite simple, but it was difficult to discover. But Edwin managed to discover it. He produced a correlation that was quite convincing, even for the limited range of a 100-inch telescope, 2.5-meter telescope at Mount Wilson. But very quickly thereafter, it was realized that this linear relationship was correct. And now that we've measured objects at a distance on the order of 10 billion light years, that's really quite a ways. And that is considered to be a measurement back of 10 billion years, since those are light years. 10 billion light years would mean that the light has been traveling for 10 billion years. What is interesting about the measurements being made right up to the present day, in an attempt to get back to what is considered to be the beginning of the universe, certainly earlier in the history of the universe, the light that reaches us is really coming from a different time frame, is it not? Even so close an object as Sirius, a star, is less than 10 light years away. But that light took about 10 years to reach us. So it is fair to say that the light has been traveling for 10 years. What is not correct to say, and I've heard this said dozens of times by careless astronomers, they're trying to impress youth and other people who may be easily impressed by a pseudoscientific view. When you're looking into the night sky and you're looking at things that are various distances away, you are not looking back in time. I've heard that said. It's a very, very careless mistake to say that, but astronomers will say it, that you're looking back in time and seeing how the universe used to be. That's not true. So, what has astrophysics discovered about deep space astronomy suggesting anything about the origin of the universe? Well, I have made some strong suggestions, but the Big Bang is completely incorrect because of a misreading of the redshift. Because the redshift is easily mistaken for Doppler shift, the early physicists, who were not astronomers, they're mathematicians, and so they made a fundamental error in interpreting the redshift. They believe that it means that everything is expanding away from everything else. That's ridiculous. That's actually anti-scientific, and nobody ever should have gotten away with saying that. Why then does that myth persist? It's the only myth we have. There's no contender. So it's the same as with natural selection. Even though I have disproved the Big Bang, and many scientists are aware that it's a stupid notion, they are not able to formulate what the redshift might mean. And as a scientist, a modern scientist, you're expected to know. So the same thing happened with natural selection. That's been thoroughly disproved, and it never should have been entertained as a reasonable theory. It's anti-scientific. But there's no other theory for the origin of the ecology, or, more importantly to many humans, the origin of humans. And the scientists are expected to have an explanation that it's at least not religious. Nobody wants a religious explanation. Well, in the case of the origin of man, there's the Bible and other myths from the past. Not to say that a myth is wrong. Very often a myth will turn out to be correct. I used to think that UFOs were myths, even though I studied the Bible, which deals almost exclusively with aliens. But whatever. That is, alien relationships with the Earth. So this matter of religion and science having nothing to do with each other is patent nonsense. But in science, we want to exclude myths. Well, with natural selection and the Big Bang, it's obvious we can't. So it's not really... In the case of the Big Bang, it's not harmful, I would say. But it would be better to know the truth. We are after the truth. So, what we're doing here is attempting to produce a sphere. And I want to show you how this... But if you're clever, you'll see what I'm doing here. That is an equation that produced a sphere. You can see it there. It even... You see that it actually put it into another form that's easier to read, a matrix form. It's a single column matrix that represents X, Y, and Z. So there is our sphere. The way that was done was with this called a surface command. And I want to show you quickly how that works. You have to type a capital S. It is case sensitive, but once you get to surf, it realizes what you're trying to do. There's several surfaces that you can draw. This is the one we want, that is the parameterization for, in this case, a sphere. You'll see that it shows that you're going to want to type in 3 expressions, and then there are some more values. This may look complicated, but I guarantee you it's not. All of these parameters can be changed. That gray plane can be removed. A lot of things can be done here, but this is the default, and we're going to leave it that way for now. So for now we have a radius. We also want to create a function, and we're going to call it x, and that's in order to make it easier for us to type in all of these values. The first 3 are functional. This one is 1, and that's for the x value, and you'll see it down below. It shows it in the single column matrix. So this is really quite an interesting program. I think I hope you're impressed. I just want to give you... We're going to be using this in order to show perpendicularity in spherical space. My discovery in 2022 that orthogonalizes space and time the way Albert Einstein showed it. He orthogonalized space and time, but with a four-line linear solution. We want the same thing, but I will show it to you in geometry. The geometry of what Albert Einstein discovered, in order to get the correct solution without 4-tensor calculus and, of course, hyperbolic space, both of which are mistakes. So first of all, we want an x function. X, and here, instead of using t and v, I'll have a link for the man who demonstrated this to me on a YouTube video. Way down here in the lower left-hand corner, you'll see a keyboard. And traditionally, this is called theta. And then I can type in a comma. And then psi is considered to be the second. And that takes the place of t and v. So our x function, we can now define it as radius. This will assume that you want multiplication if you just type in a space. So I'm going to do so. Cosine of theta followed by sine of psi. This is the typical way to do this, but look at that. Look at what it drew. You can learn a lot even by making mistakes on this thing, I found out. And you see there's a red dot there, a magenta dot. We don't have to look at that. We don't need it. These are just support functions. Now here I'm just going to do a quick copy paste, which is Control C, Control V, and that took care of those two. And now for this we want radius. That 3 up there at the top line for the first surface function, that's radius all 4 times. So this just makes it more flexible. And now we want sine and sine. Sine, although it gives us that funny deal again. And now we can type out the surface function to get another sphere. By the way, that sphere hasn't gone away. There it is. We just aren't showing it. So this is quite versatile, I would have to say. This is using the functions that were created here and here. I've also set the theta equal to 1 and psi equal to 1. These are basically the longitude and latitude and polar coordinates given as angles, the two-angle formulation which we use for longitude and latitude on Earth. Here is just a simple tau is equal to 2 pi, so we have that value which we'll be able to use down here. And just to describe what this will produce a sphere. There it is. But this is what I typed in for the surface function. This part is the x value. Sorry, it highlights the whole thing there if I'm not careful. That's x. This is y. This is z, and you see I added the radius. In the two functions that we created, radius is already included, but here it needs to be explicit. And the next 6 values are really just 2 range values. One for theta, which is 0 to tau to get the whole equator, equatorial. Tau is the value of a circle circumference. This is psi, which is half that for latitude, and therefore it only goes from 0 to pi. And so it will draw the sphere according to these 2 parameters, or parametric instructions for what part of the sphere to draw. This would draw all of it. That is, these 2 range values indicate that we want the whole sphere. These 3 are x, y, and z. So that's rather simple, and I find it remarkable that it also gives, I don't believe I can highlight this, no, but you'll see below it has a transliteration to a 1-column vector form that's x, y, and z. So that's pretty nifty, I would have to say. Could always get rid of this if we don't want the keyboard any longer. I have taken the liberty of adding, with the radius up here, you'll see that it has a slider. Now currently we're not showing the sphere, so let's turn it on. There it is. Over here you'll see some ability to change values. If you don't want to see that, this gives a more robust view. This also can be maneuvered. You can see it has several excellent characteristics. You can rotate it. This can also be animated. But you see there's quite a bit of capability here. So this is excellent for adding to this or using this for descriptions. We'll be using a sphere similar to this in order to show perpendicularity on the sphere. But you'll see the x, y, and z axis. The z axis goes up and down, and the x, y are red and green. I've also put in a label, sphere. This is our generator function, so while this box is highlighted, you can now click on the 3 dots on the right hand side and get settings, and there you get this. And then you can turn it off or you can turn it back on, And with this, you see there are several ways to show the label. I've set it to caption, which means that it will use this value under caption, or I could have it set to name. And these various checkboxes allow you can add text or show the object or not, show the label or not. All of these parameters, including the color of the label, the color of the axes, and pretty much anything that you wish to tweak can be tweaked. I consider this to be a top-level program. It's remarkable that it's free for Windows and for macOS. And I hope you enjoyed this. We will be using this in upcoming lectures to show the perpendicularity on the sphere, which, as I began to say, is already exemplified in the three axes which run through the sphere at exactly right angles. And what I'd like to point out to you, to give you something to think about, is that each one of the three lines, which we call X, Y, and Z, or Z, all penetrate the sphere at right angles, but you can extrapolate that. In the spherical geometry system and the spherical number system that I discovered in 2022, there can be considered to be not three lines running through the center, creating a Cartesian grid, but instead consider all the lines that run through the center. That is one line. All the lines that run through the center of the sphere are one line called the radial line. That's my name, and I believe that's a good name for that line. Obviously, it's not exactly what we would call a line. However, and this is what I want you to think about, it is exactly what the universe considers to be one line. It's all the lines that we consider to be straight lines, all of those coming out from the center at once are one line. And that describes gravity perfectly. I want you to think about that seriously, and a little more advanced deep thinking will lead you to realize that the radial line is perpendicular with the sphere, which means that the sphere is a perpendicular line to the radial line. You will come to find that those two perpendicular lines, one of which is the sphere itself, and the other one being the radial line, those are perpendicular. Albert Einstein showed that time and space are perpendicular. You realize that because he added a fourth orthogonal line to space, that is our spatial grid, but by making it imaginary, he was able to name it time, and therefore time is the imaginary fourth orthogonal axis. That is incorrect, although it is the correct solution in linear algebra. We want the solution in spherical algebra. I hope you've enjoyed this brief introduction to GeoGebra, and to close this out at 40 minutes, I'd like to point out that if you would like an excellent, a superb introduction to GeoGebra, the name of this program, I recommend the work of Norman John Wildberger of Australia, a professor who has attended a couple of highly prestigious universities. I forget the name of the one on the East Coast, but it's either Yale or Harvard. And on the West Coast of the United States, he attended Stanford and was a teacher there. And then he moved to Australia, and I have seen just about all of his videos. He is quite prolific in his release of videos, but he's an extraordinary geometer. I believe that he is the finest geometer on the face of the earth today. at least for the reason that he recovered rational trigonometry. An extremely daunting and difficult task is to demonstrate the efficacy of rational trigonometry. He is the world's foremost expert on rational trigonometry. And I'd like to point out that it's practically a fool's errand in today's modern, fast-paced industrial science milieu to try to get anybody to pay attention to such a major breakthrough as rational trigonometry. I'm very proud and happy to be able to say that I have a much better solution than rational trigonometry, because rational trigonometry still uses straight lines. We no longer can do that if we want to understand the universe, because the universe uses spherical geometry. The reason we want to study the sphere in terms of perpendicularity is because of Albert Einstein's discovery of the orthogonality of space with time. That is the orthogonality of the radial line with the surface of the sphere. And if you would like more information on that, my lectures going back through December, for the past 3 months in other words, summarizes over 250 video lectures worth in 2022 that I used to come up to speed in giving these presentations. From now until the solstice, I will be explicating, describing, and explaining and applying the new spherical geometry which unlocks physics. And I hope you'll be tuning in for that. And I also hope that you're going to have a great deal of fun. At least as much fun as I've had, although I don't know how that's possible. I'm the happiest man in the world right now. But this program, Geogebra, will enable us now to tackle this incredible task, which should be a delight. Science is nothing if not the art of simplification and providing understanding. We'll use GeoGebra, and I'll also be showing you some geometric algebra, which, although it is linear, it is the absolute zenith of linear algebra programming capacity. It's miraculous, and it's being used in robotics. We don't want linear algebra. We also don't want to get rid of it. There's a lot more ahead. Stay tuned to Anagalactic for further videos on this brand new geometry, number system, and algebra, which provides for us, for the first time in human history, at least 3 major goals in the study of heaven. I'll be outlining that in the next lecture. Stay tuned to Anagalactic. Thank you for those of you who are listening, and I hope that you benefit enormously from this. We'll be right back.